Hi everyone, I'm Amit Golander, Plexistor CTO. In this section I'm going to talk about big data or in-memory compute or NoSQL. I'm going to mix those terms when implemented on top of software-defined memory. So we'll start with some history. We're going to go back in time a full decade or so to where in-memory compute was starting to gain momentum. I'm not sure what the exact date is, if there is one. But basically, the technologies that storage technologies or medias that were available at the time were those two. I mean, the common ones at least. We had hard drives. We had DRAM. Obviously, hard drives are cheap and persistent, and memory is fast. And that's basically the trade-off between the two. And traditional databases, for example, have been using both of them for a very long time. I'm not going to state the exact number of decades, so I don't get a comment about that. But both of them are being used. DRAM was used as a caching layer on top of that. So basically as a read cache on top of the committed data for the single truth of the data itself, which was on hard drives, right? So that's been a very basic assumption. That's how databases work. That's how operating system works for a very long time. Now, what happened with the usage patterns basically is that with social media, with Internet of Things, with those types of applications, basically the ingest rate was just going up the roof, and the traditional solutions were not good enough. And something else on top of just caching and on top of just scale up on a single node needed to occur. And they went to a different approach that basically uses, well, first of all, going to scale out solutions, so using many nodes and the aggregated power of those nodes. And secondly, basically giving up on the persistency of the data, or at least temporarily giving up on the persistency of data and taking some risks that are not generally applicable to anyone. But for those particular use cases, at least 10 years ago, that was fine. They needed to build a solution. So what they basically have done is that they looked at their data. They said, I need a very fast ingest rate. I don't have a choice. I need to build a solution. May the cost be as it may. It doesn't have to be very efficient, but it has to work, or at least work for periods of time, and I can crash and maybe lose some data and reboot the system and make it work from that point on. So they gave up on storage, at least storage in the enterprise-grade storage fashion that we're used to thinking of. Right? They still use local file systems, as I mentioned earlier. And they moved the working set, the active working set, to memory. Now, what that basically does for the application developer, for the middleware developer, like Couchbase or Cassandra or whatever other middleware, I saw research, there's 150 different in-memory compute middlewares. Each one of them has their own implementation. What I'm showing here is just a very generic one, mostly compliant with the middleware that I saw. What they typically do is they have their own memory table or area that they store the active working set on. It's volatile. They're taking risks on that, but that's actually where they expect most of their I/O traffic to hit. Then they also, because the DRAM is very expensive, what they do is they use traditional storage file systems, and basically every once in a while just move a pretty large chunk, immutable chunk, being written sequentially to storage so it can handle the throughput. And then you have this really long list of immutable objects on the storage that if you miss, basically if you miss the memory, it's not within the active work set, you have to go down and start looking through all those versions that are in all the immutable objects which is a very painful process. So what they did is they have two remedies for that. One is compaction. So every once in a while, there's a very CPU-intensive process that goes through those chains of immutable objects and starting to merge them together, get rid of some of the older versions, get rid of data that was removed in the meanwhile. And then also there's very complex data structures here that basically kind of lead you to a subset of objects that you have to search in if the data that you're looking for is not within the working set, is not within the memory table. So you have to search through fewer immutable objects to find that value that you're looking for. Okay. On top of that, you also have a commit log, because everything here, obviously all the working set, the entire working set is in volatile memory. Well, hopefully the entire working set is in volatile memory. So you have another commit log, and you're not committing every piece of data that you're ingesting because you just can't handle that, even with SSDs. SSDs don't really change the gap. Flash technology doesn't really change the gap between DRAM and traditional storage media. But usually the SSD goes into the commit log where you actually want to, so instead of committing every several seconds, they now commit every tens of milliseconds or something like that. So the entire architecture is very complex. It's very resource inefficient. I mean, both on DRAM, you need a lot of DRAM for that to cover, aggregated across the cluster. You need a lot of aggregated DRAM resources to cover the entire working set. The working set is something, it's nice, actually the colors choice is not really great for the projector, but it looks better on the screen. Anyway, the active working set size is active, it's dynamically changing, and you kind of want to over-provision your DRAM resources to cover most of the time, most of the cases. So it's very expensive. You need to cover the entire working set plus some over-provisioning on top of that as well. It's expensive in CPU resources because you're doing compaction a lot of the time, and the read latency, which was primarily the main feature that was required, basically went away, because if it's not in the memory table, then you're going through all these different objects and searching for the data. So it's not really the read latency is not really that great, or not great as it could be. And then you're also putting data at risk with the commit log, because you're basically giving up on persistency for everything. Just every period of time, you're going to persist everything that's been accumulated with that period of time. Right? So not the best architecture in the world, but given the storage medias that are available before SDM, and giving some of those compromises, the cost compromise, the data at risk compromise, the slow recovery time. If there's a power failure and the entire memory table goes away, you need to basically recreate that, and that takes time. And then there's also unpredictable quality of service. I'll show some examples in a couple of seconds. Actually, in a couple of slides, not seconds. So that's in-memory compute 1.0, right? So kind of suggesting that there's a better implementation here on the horizon. So with storage class memory, basically storage class memory fits here, right? It's DRAM speed or almost DRAM speed, depending on the exact technology that you chose. And with SDM that basically wraps the multiple layers in a transparent way to the user, you get this new option. Now that can handle high volume ingest rates. It can put all of them in a persistent fashion, so you don't have to put the data at risk. You can have a reasonable cost because you don't copy the data multiple times. You don't need all the facilities that you had before. And you don't need all the DRAM that you had before, because the price to going to a second tier is much lower because it's integrated to the same software stack. It's not application level tiering, and then it's a single solution. It looks like a single file system, so it's also transparent and easy to use, and that's a big and here. I mean, it enables very low latency reads. The reason I put enable because we need to distinguish between two different use cases, right? One is an end user view, which basically uses some middleware that they didn't write themselves, and they are strictly forced to use the configuration options that exist today, right? The other angle is the developer view, which is someone modifying an existing middleware or writing a new one from scratch. And then they have more options, obviously, and they can do things differently, and they can implement the data structures in a very, very different way, less complex than what I showed earlier. So the first case would be just, to stick SDM wherever I had storage or memory before. And the second approach is basically going to, let's say I have the ideal storage now, which is SDM, and I'm just going to rebuild my entire structures on top of that. Okay, some examples. So OOB means out of the box, right? So I'm going to focus mostly on these types of scenarios. And the reason for that is that SDM is a new technology. So we have to fit into existing frameworks before someone will take the chance and write something new. I'll show one example of that as well with Ampool, which is a startup that does that. But most of my examples are going to focus on this area over here. So, starting with Cassandra, which was hinted before that doesn't need persistency. So Cassandra may not need persistency on the single node level, but it does need a lot of DRAM, right? And you can basically see in this graph what happens when the working set size to memory ratio, right, changes. So as long as it's underneath 1, so there's more DRAM, aggregated DRAM, than the active working set size, performance is really great. It's actually above the roof. I didn't want to show that because otherwise you can't see what happens later on when the working set size increases, or when you actually don't want to spend that much money for DRAM, which is a very expensive resource.
No, we understand log scale graphs.
So this is not one of them. So what basically happens with traditional Linux, right, is that your performance basically degrades very, very rapidly. You're talking about two different software stacks. One handles memory, one handles storage. If you have some latency objective, like in this case, which was under 10 milliseconds for the application on top of Cassandra, if that's basically your limit, you can see that you can do with maybe measly throughput for 2 times the working set to memory size ratio. But if you go beyond, but if you go beyond that, it's basically 0, right? So there's if you're using the traditional Linux software stack, you want to make sure you have as much DRAM as possible. Right? You don't have any slack to basically cut that down.
What's the back end of this? So do we use network? Do we use RDMA? What?
This is a local node. The
local.
Cassandra works on top. The benchmark Cassandra and the storage layer work on the same node. Right?
Okay.
There's no network or anything in this example. That's additional challenges for whoever is deploying that on top of that when they use a cluster. But for this analysis, you don't really need that. I mean, that just gets in your way.
No, but the salient part of Ariane's question and my feeble attempt at humor is the size of that delta is going to depend on the performance of the back end, and you haven't told us what the back end is. Right?
So this is the hardware here is an i2 4 extra large instance on Amazon, right? And we have white papers
It's using SSD.
Okay.
Yeah.
That's
okay, that's the question. Yeah. Of course, it's using SSD. It's using actually
because you could
four
have made it look a
SSDs
lot,
in this
could have made
example.
it look a lot worse if you were using a 7200.
That's not my objective. Everyone looks a lot worse anyway. I don't need to make the effort to present that, you know, in
Yes, but your
compared to tape.
refreshing honesty disturbs us.
Yeah, we expect you to make yourself look as good as you can. That you don't try is strange to us.
So I assume if the differentiator was not as big, I would have done that as well, right?
Oh, yeah.
I just don't have to.
Remember, we deal with EMC on a regular basis.
Some of my best friends are, no, I'm just kidding. Okay, so we don't have a lot of time left. I'm just gonna say that each one of them, well, I think not each one of them, but most of them have a white paper on our resources tab in the website. So whoever is interested in learning more in a particular use case can go and look at that. There are multiple pages, and they describe everything with all the little details and the exact command line, so everyone can recreate the test by themselves if they want to. So scientific level comparison, not marketing level comparison. Okay, benefit number 2 talks about persistency, right? So benefit number 1 was large working set, saving money on DRAM and on the cluster size in with SDM. The second one talks about persistency. Now, there's a reason why originally, and actually for today, NoSQL or in-memory compute or big data is kind of limited in its usage. And the main reason for that is that it has the assumption that you're willing to lose some data. Now, it's perfectly valid for many use cases. Maybe I can lose some likes, you know, on my Facebook. It's not the end of the world. Maybe some users will think it's the end of the world. I mean, that really depends on the personality of that person. But for other use cases, persistency is key, or durability is key. And what you see here is a traditional, this case is MongoDB with SSD in the back, like all the other examples. And what you see here is basically that if you're configuring the server to be last transaction safe, so basically not lose any data on per commit, right? Your performance is going to degrade by an order of magnitude, right? I mean, this is the performance level with XFS, with MongoDB on top of XFS. This is the performance level of the throughput where you settle for losing data every once in a while for eventual persistency. And then the blue bar, well, the solid blue bar, would be the performance on the same exact software and hardware if you do require last transaction safety, right? So this really explains why MongoDB users or any other NoSQL users basically don't use persistency, right? They don't use it for or at least it wasn't really built for scenarios like that, because you pay a lot in currency, in performance currency, for requiring persistency, and that limits the usage of the platform as well. That doesn't mean there are some people obviously who do that and pay more in resources, but most users knowingly or unknowingly risk their data, at least today. Now this would be the comparison between XFS and SDM. In the yellowish, I'm not sure what that color is, orange, whatever. That would be the same results as here, just slightly different, the scale is slightly different. And the blue bar is basically, you can see that it kind of restores the original performance. And the main reason for that is that within our software layer, there's no difference between synchronous, asynchronous, direct I/O. I mean, everything is the same. Everything is always being written synchronously to the device, because there's no point doing something else with SCM technology. But at upper layers within MongoDB, etc., there are different assumptions that can be optimized. Actually, can be optimized by at least 15%, as we saw in some benchmark. So performance can actually be higher than what you see here, but at the moment, at least out of the box, because we're maintaining two separate persistent copies, one in the commit log and one in the data itself. Both of them are fully persistent without any good reason. But just because of its out-of-box comparison, you can see that you can basically restore the entire, well, the throughput that you were used to while adding the requirement for persistency. Then you can also see that latency improves dramatically, both the average, the 95th percentile, the 99th percentile, whatever flavor you want to look at, increases, well, not increases, actually decreases its latency, but improves dramatically. Another, I'm going to run through them because I have 4 minutes left. So another benefit is rebuild time, basically shortening the rebuild time. This example is with Couchbase 4.5, so the very new one. You have a cluster of Couchbase servers. You have clients working with that cluster server. One of the nodes fails. You need to basically rebuild another server node to take ownership of all the data that was lost and all the transactions that were lost. And that adds, on top of the traditional load from the clients, that adds additional load on rebalancing. Now, obviously, not all the bottlenecks are associated with storage. Actually, most of them are associated with the application itself. So
is this using the Mellanox RDMA connectivity? Or what is the network connectivity between the...
So this example, no, we were not leveraging RDMA. Well, depending on which line you look at, right? This is not a specific benchmark yet. It's not published yet. But basically, on a qualitative measure, right, not a quantitative one, you have two things that can basically improve your performance. One is removing the storage-related bottlenecks and just, having to suffer with the traditional application level or middleware level rebalancing bottlenecks. That would be number one. That would be the out-of-the-box configuration. And then an additional option, like you mentioned, is basically recovery via a brick. So instead of having, for example, 3 replicas of the data within Couchbase, you would have 2 replicas within Couchbase and then a 3rd replica within the storage layer, which provides you a better rebuild time on one hand, and also 0 downtime at the application level on the other hand. Right? So kind of a mix of those two. Okay. An important one. This is actually a different color scheme because it's a screenshot I received from a customer, and it's not the NoSQL. It's MySQL in this case. Again, because it's not focused on everyone can download it and use for whatever application they want. So it's not focused on our main, business focus at the moment. But you can see that in MySQL, even though the load is fixed, I mean, they're not trying to get as high as possible. That's not their intention here. You can see all the blue line is XFS. Well, actually, ext4, I think, in this case. You can see that there's the standard deviation is really high. Depending on the exact moment compared to whatever, the garbage collection within the page cache within Linux, you get very different performance, almost, a full swing, almost 50% different. And that's probably not a desired property. And the same load generated with on top of SDM basically provides very consistent steady state. Besides this, don't look at this one, but across the period of time. This is a period of time of 2 hours. So that's the predictable quality of service, and we've seen this. Actually, we've seen this with the Redis example before as well. Right? If you remember, if you don't come to me later on, I'll show that again. And then a 5th example. That's not an out of the box. That's actually a new middleware that Ampool, which is a startup, is building. They're based on Apache Geode and several other things. They have a pipeline of different solutions that they're maintaining. Everything has to be fully persistent. But the important thing is they have this single storage place where they go back to every time and again, and then they can restore everything from whatever point within the data pipeline. And that's from their demo, basically showing 56 times speed up with SDM compared to XT4. Even though they have enough, memory available and everything else is kind of stable, they still get the 56 factor in performance improvement. And with that, with 20 seconds left on the clock, I'll invite everyone to go and read the actual white papers on our website.
Can I ask one quick question? I know
Sure.
we're literally down to the seconds, but how many customers have you got, and how is it actually going in the market? I mean, I think we're all hugely impressed about the smoking fast performance and the replication, but yeah, how's it going from a sales point of view and customer point of view?
I'll let Jeroen answer.
The product is still in beta. Customers are testing the product. It's in the range of the tens, a bit more than 20. We don't have any revenue yet, of course. We are expecting the first PO to come during Q4.
Okay.